Hello, everyone. I wanted to go over the characteristics or the nature of gases and also pressure, because gases exert pressures in different ways. So here we go. The characteristics of gases, as you can see on the screen here, they have an indefinite volume and, of course, an indefinite shape. We know that gases, the particles are actually not touching. They're what's called a non-condensed state. The particles are actually flying past one another with tremendous distances between the actual particles themselves. So they can expand to take the shape of any container they want. So without, not only can they expand, which means they have an indefinite volume, but again, that expanse means they can take on any shape as well. You must have a closed system to contain a gas. You do have to put a cap on the bottle, in other words, or somehow enclose the gases inside of a container. We call gases fluids, which means they can slide past one another. So liquids aren't just fluids. Any particles that can slide past one another, or in other words, not locked in bonds, we call them fluids. Gases typically have a very low density. There's not too many particles per space. So if they don't have too many particles, the mass is quite low per the volume that they occupy. And of course, they can exert a pressure. Okay, so let's talk about pressure here. Pressure is actually a force, a push or a pull over a space, or over a two-dimensional space. So this is actually a push or a pull, and this is actually a two-dimensional space, so that's a flat sheet. Okay, so how does it push? How does it pull? Well, we can imagine, if you think about this, pushing on a flat sheet. If you were to take your whole hand and push on this flat sheet here, so this is your hand, and push on this flat sheet, and you push down, with about 25 pounds of force. So 25 pounds of force downward. That whole thing is spread out over your whole hand. 25 pounds is over your whole hand. So we would expect that a 25-pound push over this area, over a wide area, is going to give us a small pressure. Okay, a small pressure. Now, you would think, well, isn't that a big pressure? No, because again, it's the force over an area. So once you take that force, 25 pounds down, and you spread it out, that gives us a small pressure. So don't mistake pressure and force. Pressure is force over an area. Force is just a push or a pull. Okay. Now let's change this, and let's take the same 25-pound push. 25-pound push down. Here's our flat sheet of paper, but now let's make it like a screwdriver. Okay, so here's a screwdriver. I know it's a terrible drawing, but there's our screwdriver, and we're going to push straight down. Now our force still 25 pounds, but it's over this little tiny spot right here. Okay, so now the area goes way down, which makes our pressure go way up. Okay, you're going to say, but I didn't push any harder. I know that's a push or a pull, which means it's a force. But the pressure, which is that force over an area, gets much larger. So again, if we talk about a woman in high heel shoes versus an elephant walking on linoleum floor, I've talked about this before. If this is an elephant's foot, you got to think that 2,000 pounds is pushing over this. I don't know what that, let's say it's 144 square inches. I know it's not, but which inches squared. So that's 144. Hold on, let me get my calculator real quick because I'm kind of going on the fly here. So 2,000 pounds. So that's 1 ton over 144 square inches is 13.8 pounds per square inch, or 13.9 pounds per square inch. That's the pressure. Okay. Now, if you take a 150-pound woman, okay, that's just a best guess. Don't worry about it, ladies, or men, or whatever. 150-pound woman. And now we have a high heel shoe, which is if you take a high heel shoe, let's say she's stepping anytime all on the heel. So if the heel is, well, let's say it's a real skinny heel. Let's say it's like a ½ inch squared. So that gives us 0.25 inches squared. So 150 divided by 0.25 is 600 pounds per square inch. That's not something you'll survive. Okay, so don't make anybody mad wearing high heel shoes. Okay, so notice the difference. The pressure, since it's spread out, is 13.9. Since the pressure is not spread out, it is quite larger. Okay, so that's an example of pressure versus force. Oh, by the way, the way that they found atmospheric pressures with this thing right here, which is called a barometer. It was actually invented by Evangelista Torricelli. And what we're seeing here is that, let me get rid of this. What we're seeing here is that these atmospheric pressures pushing down, okay, on this open bucket of, he used mercury. That's pushing the mercury up into the tube, causing the level to rise. So on high pressure days where there is a gentle flow of air down, again, it's not a wind, but it's a gentle falling of air, it pushes up, it pushes down on the, on the surface of the liquid, which forces the liquid up into the tube, and we have what's called a high pressure system. High pressure systems tend to be nicer, warm, gentler days, okay? Now, if you have a low pressure system, that means cold, moist air, it's typically warmer air than the air around it, is gently rising. So now the air is gently rising, and now you have a lifting up off of the surface of the liquid, and the liquid level falls. That's a low pressure system, and those tend to be your nasty kind of garbage rainy days and stuff like that. Storms especially are low pressure systems. Okay, so that's the barometer. Moving forward, okay, I don't want to necessarily talk about that, so let's move forward here. We'll talk about that in class. Okay, now pressure can take on several numbers depending on where you're at in the world or what you're consulting. For science, we will typically say that pressure has a one atmosphere. That's standard pressure. Okay, standard atmospheric pressure. But 1 atmosphere is also equal to 760 millimeters of mercury, or 760 torr, or 101.3 kPa. That's kPa in pascals, and this is used in America, which we will not use at all, okay? So as far as the conversions, you just have to know the conversions between these, okay? So if we did a couple practice problems, and I took 0.357 ATM, and I want to convert that to torr, and again, we'll use dimensional analysis here. Based on the last slide, we know that 1 ATM is equal to 760 torr, so you just have to multiply by 760, okay? So 760 times 0.357 is 271. We'll stick with sig figs here, 271 torr, all right? Converting from torr to atmospheres, or let's jump down to this last one. If I have 147.2 kPa, and I want to convert that to torr, I know that 101.3 kPa, and yes, if you're thinking, do I have to memorize those? Yeah, you do. So make sure you memorize the pressure equalities on the last slide. I'll go back to that slide here in a second. And so 147.2 times 760, press equals, and then divide by 101.3. So in converting from kPa to torr, we end up with 1,104 torr, okay? That's equal to 1,104 torr, okay? I didn't necessarily stick with sig figs there, but we're okay. All right. All right, so that's that. That's converting between these. And again, let's go back to this slide right here. Of course, we do, all these things are equal, and yes, you have to memorize them, okay? Also notice that this between this and this, it's a 1-to-1 relationship. So once you know millimeters of mercury, you automatically know torr, okay? So just keep that in mind to make your job a little bit more easy, okay? And that's it. I'll end there, and we'll see you in class, and we'll see what else we can get into.